Does anyone have their video on, by the way? I'm not getting any video, just checking.
I don't.
Okay. Yeah, when I logged into Zoom, a bunch of things changed. Sorry.
Okay, hi everybody, and welcome to our regularly scheduled multi-tenancy working group for Kubernetes. Today, Faye is going to be presenting on the virtual cluster project, which is an open source project that you can check out on the multi-tenancy GitHub page, which is part of the Kubernetes SIG project on GitHub. So he'll be giving us an update and a demo with his coworker.
Okay, so can everybody see the screen?
Yep.
Okay. Okay, let me get it started. So today, hi, my name is Fei. I come from Alibaba. So I'm working on the SIG multi-tenancy, one of the incubator project, which called Virtual Cluster. Today, I'm going to do a quick introduction or briefly describe the progress of this project. And my colleague, Chao, will give you you guys a detailed demo about what we have been, what we have done. So I'm assuming most people knows the concept of virtual cluster, so I won't spend too much time on the high-level idea. I just give a few sentence update about the architecture and to refresh your memory. So today's presentation is more about the exactly things what we have implemented in this project. So the reason that we want to come up with a virtual cluster is try to deal with the case that in case tenants needs hard Kubernetes multi-tenancy. So we kind of solve this problem by providing dedicated control plane for each tenant. But unlike other solutions like virtual kubelet, they connect to use virtual kubelet to connect to other pod resource provider. So in our model, the pod resource provider is Kubernetes itself. So here I just, this diagram is one of the blog posts that have been posted last year. So I'm just leverage this diagram to give a very quick describe of the overall architect. So essentially you can treat virtual cluster as a kind of extending current namespace-based isolation mechanism. Basically provide each tenant a class to view. In short, so each tenant will have a dedicated control plane, which we call the tenant master. And we have a developer syncer, which is a kind of controller to synchronize the object that needed for pod provisioning from tenant master to the supermaster, which is actual Kubernetes that manages the physical resource like nodes. So the high level idea is from a tenant perspective. So they probably don't even know that they're running in this kind of hierarchical level. They just assuming they have own a dedicated Kubernetes. They are not aware of the existence of the supermaster at all. This is our ideal case. So now in this project there are three major components that we have developed. The first one is the VC manager, which actually is a controller trying to reconcile for CRD, which is called virtual cluster. It manages the lifecycle of the tenant, the tenant master components like API server, controller manager, etcd, and all. So for the tenants, we don't install a scheduler because in this model, the whole scheduling things is done in the supermaster. The tenant doesn't need a scheduler at all. So this is a controller that you can think of, manage the lifecycle of all the tenant master components. The second one is the syncer, so which is the centralized controller that populates the API object needed for pod provisioning from tenant master to the supermaster. It also, take in charge of the updating the object status back from the supermaster to tenant master. So thereby the tenants can see the overall progress of the pod, pod creation. They know exactly. So they know they kind of get an idea what happening in the super, but not indirectly. Just they can only view the status of the objects in the tenant master. We also, this single controller also needs to periodically scan the synced object to ensure that the states between the tenant master and the supermaster are consistent. Because we need to take care of a lot of corner cases like sync restart, sync crash, tenant master restart, tenant master crash. Or in all these corner cases, the syncer need to make sure the data are still consistent. The third component, which we call is VN agent. This is a node daemon that simply just proxy all the tenant Kubernetes API calls to the actual Kubernetes process running the node. Because in our model, so the tenant is supposed to only query the paths that belong to himself. So the VN agent need to ensure that, okay, if there is a pod request, pod API request, the target path has to be owned by the tenant by the tenant. So this kind of isolation, this is kind of provide another level of isolation. Also work on a problem such that the Kubernetes can only be registered to one master. They cannot serve multiple tenant master at all. So so this is the page that in the GitHub page. So I list up everything. Today I'm going to go through most of the content in this major README. There is a short demo here, but this is one. We are not going to do much more than this short demo, but this is a good start for very simple idea what we have implemented. I also added an instruction, which is a more details, kind of very detailed steps. I'm not going to go over all this because Charles' demo, we repeat most of the steps that I have mentioned in this instruction. Okay, so next I'm going to briefly talk about from the users or the actual user perspective, what are the things that we supported and what are not supported? Because so when we design this, we're trying to make Kubernetes API compatibility, retain the Kubernetes API compatibility as much as possible. Indeed, we have tried we have tried to run the virtual cluster against the Kubernetes conformance test. Most of the tests actually pass, and there's one failure because it's kind of hard to support the subdomain API if somebody knows what it is, because you cannot enforce that the supermaster and the tenant master have the same subdomain. So this is the one that fails. Besides the Kubernetes conformance test, because to me, they are still a kind of limited scopes of the test. There are some other parts that we want to tell the users or want to let the users aware of something that virtual cluster that cannot be supported. For example, the virtual cluster kind of follow a serverless design pattern, which means we don't want to expose the entire supermaster node topology up to the tenant master. So let's say if supermaster has 10 nodes, in our model, the tenant master won't show 10 nodes. They only show, the nodes only shows up once the pod actually is bound to a particular nodes in the supermaster. That being said, if there is no pods running in the tenant master, no virtual node will be shown. And this also means that virtual cluster.
Question at this point?
Sure.
I don't know how much of a question you want to take here, but you've introduced a new allocation problem here. I think you said that each node is owned by only one tenant. So there's an allocation question of how do nodes get assigned to tenants?
Sorry, node is not belong to you. This node, what I mean is a virtual node object shows up in the tenant master.
So the real nodes on the super cluster, they're serving multiple tenants. Is that right?
Yeah, shared by multiple tenants.
Okay, thank you. Sorry.
Yeah. That's the main motivation of this actual project. We want the supermaster nodes shared by all the tenants, but in the tenant, from a tenant's perspective, they only show a virtual node that they have pods running. There's actual pods running in that virtual node. In the demo, I will give you more details about what does this mean. But on the other hand, what I mean is the virtual cluster doesn't support daemon set-like workloads in the tenant master. Because daemon set assuming it will run a daemon in all the nodes. this will introduce a lot of problems if you want to support it. So in other words, so if the syncer controller will reject a newly created part if the node name has been set in the spec. So we will going to simply reject at this point.
I understand. Thank you.
Yeah. So another thing is the syncer doesn't update the node list objects in the tenant master, because nowadays Kubernetes mostly relies on node list to do the heartbeat update. So in other words, the virtual node we updated the virtual node object with the status update in the tenant master, but in a much slower pace compared to the node list update, which is happens maybe every 10 seconds. So which means if the tenant master install a node controller, it may if we don't increase the grace, node monitor grace period, sometimes the tenant node controller may report the node is offline kind of thing. To avoid, and in the worst case, the part eviction mechanism will be introduce some problem. So our recommendation is kind of increase this node monitor grace period to a larger value. So let's say larger 16 seconds, then the tenant, the node controller won't do some weird things. Okay, the third thing is the core DNS is not tenant aware. So if tenant want to use DNS, they in our model, they have to install their own DNS in the tenant master. There is a kind of hard code, contract is that the DNS service should be created in the Kubernetes system namespace using the name Kubernetes. So this is the reason that syncer needs to, by looking at the path to find the core DNS service and update the class IP into the part spec DNS config. You can, in certain sense, you can treat syncer as a very powerful and complicated webhook, because all the parts actually provision in the supermaster the spec is kind of manipulated by the syncer. The first bullet is we actually support a service, but to make it clear is if we want to support a service, make the service work in the DNS, or make the service behavior looks consistent from tenant and the super perspective, the CIDR of the tenant master and supermaster should be the same. I will spend more time later to explain more about what does this mean. Just give you a heads up. Virtual class fully support a tenant service account. So every service account created in tenant master, you will find that it actually takes effects in the pod. Another thing is virtual class doesn't support the tenant persistence volume. So which means if you install kind of the setup, the order, the persistent volume in tenant master, or you install a PV controller, your customized per PV controller in the tenant master, this won't work at this point. Because in so basically our understanding, our model is more like a serverless model. So all the tenant care most is the PVC. You just describe what you want. The actually persistent volume, provision part should be done in the super cluster. That being said, so all the PVs and the storage cluster provided by the supermaster, and our syncer will populate rows object back up from supermaster to tenant master. So if your tenant hasn't created PV, we are going to either ignore it or just forcibly delete it by the syncer. The last point is the tenant master supermaster. We recommend they use the same Kubernetes version to avoid incompatible API behavior. And the current syncer controller, all our controller built on the Kubernetes 1.16 APIs. Now I think the major Kubernetes is 1.18, so some new APIs may not be supported, but that won't be a big problem. So as over time, we are going to release our components using the latest catch up the major Kubernetes. The entire project currently, I think, is pretty mature in the sense that we have done very intensive, testing internally. I think it's pretty ready for everybody to give a try. We probably will go to release it very soon. Okay, now is my kind of briefly describe the project status. I'm going to hand over to my colleague Chao to do a kind of detailed demo to show you guys, and just feel free to ask questions during the demo. Okay.
Hey, Faye, I have a couple of questions, but you want to address them now or later? I'll just mention it, or should we just come back to it later?
I would suggest that do it later, because maybe some of the questions get answered during the demo.
Okay.
Yeah. So let me see. So Tasha, what should I do? Should I hand over to?
Should I just click the share screen or wait for Faye to quit?
Let me see. I think I will do a stop sharing, and Charles, you give it a try.
Okay.
Yeah.
So can everyone see the screen?
Yes, I can. Yeah.
Okay. So I'm going to do the demo about using virtual cluster. So in this demo, I'm going to show how to set up the management components for the virtual cluster, how to create a virtual cluster, and how to perform some basic operation supported by the Kubernetes on the virtual cluster. The demo will be done on the Minikube, and the version of Minikube I'm using is version 1.5.2, and the corresponding Kubernetes version is 1.16. There is no specific reason for using this version. As Faye just mentioned, we have tried out virtual cluster in many major releases from 1.12 to 1.16. And in the future, we will try to catch up with the latest released version of Kubernetes. Before I get started, I would like to explain some terms and settings that can help you to better follow this demo. So there are 3 terms I'm going to use frequently in this demo. The first one is the supercluster, which is this Minikube cluster, the base cluster that hosts all the virtual cluster. Second is the supermaster, the control plane of the supercluster. And the third is the tenant master, the control plane of the tenant of the virtual cluster. And as you can see, I split the window into 2 panels. So during the demo, I will use the left panel to control the supercluster, and use the right panel to control the virtual cluster. Okay, so let's get started. So in order to use the virtual cluster, first we need to deploy all the management component for the virtual cluster. And also the virtual cluster is rely on 2 CRDs. First one is the virtual cluster CRD. Another one is the cluster version CRD. I will explain the contents of these 2 CRDs later. So now let's just apply these 2 CRDs. And also this project also rely on the tenant and a tenant namespace CRD. This demo is rely on this because we assume that the virtual cluster is created by a tenant under the tenant namespace. Okay, so we have this 4 CRD installed. Next, we can start deploy the management component for a virtual cluster. For this demo, we create an all-in-one YAML that can help us to deploy all the resources required by the management component. But for the first release version, we will create a Helm chart to ease the deployment process. So let's apply this YAML. As you can see, we create a bunch of resources. You can just ignore the first 7 because that is for the tenant controller. For the virtual cluster controller, we first create a namespace VC manager. And then we create cluster role and a service account for each component. Then we set up VC manager and a VC syncer with the workload deployment. And we set up the VN agent, use the workload daemon set. Let's check the status of these 3 components. Okay, as we can see, all these components are up and running. And during these 3 components, the VC manager is responsible for provisioning the tenant master for a virtual cluster. And later, when we're creating a virtual cluster, we wanted to see what happened inside the VC manager. So let me just output a log of the VC manager. Okay. Next, we need to install a tenant CR because we assume the virtual cluster is created under a tenant namespace. So as we can see on the right-hand side, we have a namespace tenant1 admin created. And later we will create a virtual cluster object under this namespace. Next, we can start creating a cluster version. So in order to ease the creation process, we develop a command line tool called Virtual Cluster Controller, which can help user to create the cluster version, the virtual cluster, and generate the kubeconfig file required by the virtual cluster. Let's create the cluster version first. Okay, so on the left-hand side, we can see that the VC manager said a new cluster version is installed, cv sample mp. So what's inside cluster version? Let's take a look. So the cluster version is the CRD that define the version and the configuration of the tenant master's components, which include an etcd, an API server, and a controller manager. For now, we still hardcode all this configuration and the versions in this YAML, but in the future, we plan to cooperate with other working group, like cluster add-on working group, to come up with some standard operator that can help us to fetch the manifest from a remote Git repository. Okay, so next we can start creating a virtual cluster. Same as before, we need to specify a YAML file, but this time we also need to say the name of the kubeconfig file we wanted to use for this virtual cluster. Okay, the virtual cluster is creating. At the same time, let's see what's inside the virtual cluster YAML. So inside the virtual cluster YAML, we define some basic information of the virtual cluster, like the name and the namespace of the virtual cluster. Under the spec fields, we define the cluster domain of the virtual cluster, and then the cluster version required by this virtual cluster. Notice here, if this cluster version is not available on the super cluster, then this virtual cluster cannot be created. We also specify a PKI expiration day. Here we specify it as 1 year. We also allow user to specify the service CIDR. This service CIDR will be used by an API server of the tenant master later. Okay, so as we can see on the left-hand side, the VC manager is still deploying the components of the tenant master. It will deploy all these components in order etcd, API server, and a controller manager. Okay, the virtual cluster is currently up and running. And on the right-hand side, we can see that the VC controller tells us the etcd, API server, and the controller manager, all these 3 components already. Also, we generate a kubeconfig file for this virtual cluster. Before we continue, let me export this kubeconfig file. It's not necessary, I just don't want it to keep typing the kubeconfig command line option. Okay, so next we wanted to check the status of this virtual cluster. We wanted to make sure this virtual cluster is work as expected. First, we check the cluster information. So as you can see, we have a Kubernetes master running at this address for the virtual cluster. So what's this address? So since we are running this demo on a Minikube cluster, so the IP address is actually the IP address of the Minikube node. And we use a node port service to expose the API server of this virtual cluster. So the port number 31,542 is the port number of the API of the node port service. Let's check the node port service on a supercluster. So as you can see on the left-hand side, we have a node port service named API server-svc, and then the port number is 31,542. Okay. Let's also check the namespace on the virtual cluster. We have 4 initial namespace: default, no lease, public, and the system. Let's check the namespace on the supercluster. So we have 5 more namespaces. The first one is the root namespace of the virtual cluster. So what's inside the root namespace? So inside the root namespace, we have the 3 components of the tenant master running: API server, controller manager, and etcd. And for each namespace on the virtual cluster, we will create a corresponding namespace on the supercluster. The name of the corresponding namespace is star with the root namespace, followed by the target namespace. Okay, so next I will set up a core DNS on the virtual cluster. So this is not necessary, but in later demo, I wanted to show how to access a pod in the cluster using a DNS. So I set up this DNS server. Let's check the cluster information again. Okay, so the DNS server is up and running with the Kubernetes master. So by now, I have shown how to set up the deployment management component for the virtual cluster, and I have created a real virtual cluster. Next, I wanted to show how to set up a workload on a virtual cluster. So the workload I'm going to set up is a very basic Nginx workload, which consists of 2 replicas. And I also create an Nginx service to expose these stateful sets. Let me apply the YAML. Okay, let's see what happened on the virtual cluster. Okay, the container is still creating. Let's see what happens in the corresponding namespace on a supercluster. So we can see that 2 Nginx pod is up and running in on the supercluster. So if everything works as expected, these 2 pods should up and running on the virtual cluster as well. Let's check again. Okay, so the 2 Nginx pod currently is up and running, and we also have an Nginx service up and running on the virtual cluster. So now we have an Nginx service and 2 Nginx pods. So can we visit these 2 pods and the list service from inside the cluster? Let's give it a shot. I will first apply a very basic pods called cur. So I will use these pods as an interactive cur client. I will log in this pod using the cur command to visit the pods and the service from inside the cluster. I just want this pod up and running, do nothing important, so I use the initial command top. Let's check the status of the pods. Okay, it is running. Let's log into the pods. Okay, now we are inside the pods. So as Fei just mentioned, currently the service discovery on the virtual cluster is rely on the environment variables. So here are all the environment variables inside the pods. And we can see that here is the service, my Nginx service IP, cluster IP. So by using this environment variables, we should be able to visit the my Nginx service. Let's try it. Okay, it works. Next, can we visit this 2 Nginx pods through the DNS as well? Let's try the my Nginx 0. Okay, it works. And also the my Nginx 1. Okay, so in this example, I show that the virtual cluster allow user to deploy basic resource like stateful set, service, and a pod. And a virtual cluster also allow user to visit all these resources in cluster through the DNS. Next, I wanted to demonstrate how to use the controller or an operator on a virtual cluster. So before I get started, I wanted to briefly explain how does a controller or an operator work inside the Kubernetes. So the core idea of a controller is a client, Kubernetes client running inside a pod in a cluster. That this client also need to have the ability to control or access certain resource on the cluster through the API server. So to accomplish this, the client need to accomplish 2 important steps. First, it needs to get the full address of the API server. Next, it needs to prove to the API server that it has the permission to control certain resource. So to get the full address of the API server, the client can use the environment variable as well. So here are all the environment variables inside a pod running on a cluster. And among them, there are two very important environment variables, Kubernetes service host and the Kubernetes service pod. So the value of the Kubernetes service host is the cluster IP of the Kubernetes service. And this Kubernetes service is responsible for all the in-cluster API server visit. So by combining these two environment variables, the client can get the complete address of the API server. So to prove its identity to the API server, the client use the service account. So inside a pod, the information of a service account is stored under the service account directory, which includes a root certification file, the information of the namespace, and the bearer token. So each time when a client wanted to talk to an API server, it will use the information under this directory to identify itself. So in our case, on a virtual cluster, if a user creates a pod on a virtual cluster, then we will just create a pod object on the virtual cluster, and the status will be pending. At the same time, the syncer controller will notice that there is a new pending pods on the virtual cluster. It will try to create a real corresponding pods on the supercluster. But when it's creating a new, creating the real pods on the supercluster, it will use the tenant master's information to set the environment variables and the information under the service account directory. That is to say, if the pod finally up and running, then from the pod's perspective, it will feel like it is running on the virtual cluster instead of running on the supercluster, because all the cluster information it can get is the information of the virtual cluster. Okay, so enough explanation. Let's see a real working case. So let me install a controller on the virtual cluster. So the controller I'm going to install is a very basic controller. It's a pod lister controller. The container is still creating. So let's see what's inside the pod lister controller. So the pod lister controller has a very basic client set, which is based on the in-cluster configuration. And this client set will keep listing all the pods under the default namespace every 10 seconds. Let's check the outputs of these pods. Okay, it's running. Okay, the controller works as expected. It keeps listing all the pods under the default namespace, the cur pods, the my-nginx pods we just created, and itself. So in this example, I demonstrate that the virtual cluster support the controller and operator pattern. Next, I wanted to show how to use some advanced feature like persistent volume on a virtual cluster. So when designing the persistent volume, when designing the feature to support the persistent volume, we study several use cases of the persistent volume, and we observed that when using the persistent volume from the user's perspective, the most important thing is if the persistent volume claim can be successfully bound, and if they can use the persistent volume on the cluster, users normally don't care about how many persistent volume are available and how to create a persistent volume. It is the cluster administrator's responsibility to create a workable persistent volume. So in our case, we treat the virtual cluster is actually a client for the supercluster. So we believe when we try to use a persistent volume, we should create the persistent volume on the supercluster. And the user of the virtual cluster should only be responsible for creating a persistent volume claim. That is to say, if there is no pending persistent volume claim on the virtual cluster, then we will not synchronize the persistent volume back to the virtual cluster. That's the working case. So let's go back to the supercluster. I will first try to create.
I'm sorry, did you say the persistent volume does not copy back to the virtual cluster?
By default, if there is no persistent volume claim on the virtual cluster, then the persistent volume is not viewable on the virtual cluster.
Right, but if there is a PVC in the virtual cluster,
yes, correct,
and then it gets bound in the supercluster, after it's bound, does the PV get copied to the virtual cluster?
Yes, correct. The PV will be copied back. So on the left-hand side, I will first try to create a PV. It's a very basic host path PV. Okay, so we can see that the PV is successfully created and the status is unavailable. Let's go back to the virtual cluster. We cannot see the PV, but let's try to create a PVC. Okay. The PVC is successfully created and the status is bound. Let's check the PV again. This time, we can see that the PV has been synchronized back to the virtual cluster. The status is bound. So in this case, I show that the virtual cluster support advanced feature like persistent volume. The virtual cluster is aims at providing hard multi-tenancy in serverless environment. So if there is no active resource connected to a node, then a node should be deregistered from the virtual cluster. We achieve this by using a component called virtual node garbage collector, which will periodically collecting empty nodes from the virtual cluster. So last, I will try to remove all the resource I just created, and we will see what's happened. Okay. So the pod is terminating. So if everything works as expected, after we remove all the resource, the node should be collected.
Do a KC get nodes right now?
Excuse me, what?
Try KC get nodes currently.
You mean the GC try to collecting the nodes currently? Is that what
No, just show the output of KC
oh,
get
okay.
node.
The node is still there. Okay, so there is no pods running on a virtual cluster now. But node is still there because currently the default grace period of the node garbage collector is around 2 minutes. So we need to wait for 2 minutes. Since this is in the last case, so I think I can ask any questions, comments if you have when we are waiting.
I have several questions, but I'll just pick one or two because we don't have time. Firstly, congratulations. This is a very complex thing and you guys have done an awesome job. So really congratulations to you guys. Really good job. Okay.
Thank you.
Super cool stuff. But because this is so complex, there's still potential for holes, right? So I want to go back to a couple of things. One is admission control, right? Can each tenant cluster, can each virtual cluster have fully independent admission controllers, or is there some dependency on the supermaster?
Yeah, I can answer that question. So all the admission control by our design is done by tenant individually. This is, but in reality, while in production, I do see cases even internally. We have cases that we want to enforce a global admission control in the supermaster. We don't have a very strict requirements of you cannot do that or you cannot do that. By design, I think most of the admission control should be done in the tenant.
But are there going to be restrictions if tenants want to do whatever admission control they want to do? Because eventually it has to be enforced in the scheduler of the master.
schedule.
The super master, the super.
So which part of mission control are you talking about? API server mission control, or that has nothing to do with the scheduler. So everything that scheduler needs, there is a so here's the thing. So currently we don't realize if there is a CR, we only sync all the API core API resources that Kubernetes supports. We don't currently sync any CRDs. That being said, we sync all the resources that are needed by scheduler at this point. But if the scheduler needs special CRDs, we cannot synchronize it. At least we don't support synchronize those CRDs.
Yeah, there's no virtual kubelet here, right? They're running on the kubelet of the supermaster, super cluster.
Yes, there's no virtual kubelet at all. So there is a kubelet in the supermaster. So now what's your so you are saying that you want to?
I guess I was referring to admission control by the kubelet. If it takes time, we can take it offline. I don't want to distract.
You're talking about webhooks, like validating webhooks and policy and those sorts of things.
Any kinds of admission control. Yeah, basically admission webhooks.
Yeah, we understand. So currently, most of webhooks, if you have tenant can install their own webhooks in the tenant master, there's no problem because the chart has already shown that the controller actually works. Which means if you start a webhook server port in the tenant server should be able to access those ports. The webhook definitely should work in the tenant master.
Okay, and one quick clarification. Can you clarify what was the restriction about the daemon set? Are you saying the virtual cluster cannot have daemon sets, or what was that exact restriction about the daemon set?
The daemon set is because we don't fully expose the underlying node topology. So then, but if people because when you install daemon set, you probably have some already expectation. Let's say I see 10 nodes, I hope to see 10 pods to be created. But currently we don't expose the full topology. The nodes are showing up, kind of on demand. If only your pods, user pod, the virtual pod is going to show up. If you install a daemon set, there is a few problems that the daemon set cannot be auto scaling down, cannot be automatically scaled down. So my GC certainly just won't work. All the nodes will persist in the tenant.
Makes sense.
Did you mention anything about the CNI configuration and the relationship between the master and the tenant and the network policies, therefore, after that, and how they relate?
The CNI currently, all my talk at this moment are focused on the control plane. The data plane isolation is a completely different topic because I don't include it in here. But if you talk about network policy, I believe network policy, currently we don't synchronize network policy object down at this moment. Because, but that's not a big problem if you want to support that. I would say that if you create a network policy within the tenant, the network policy should be, I don't think there is a big blocker to make those network policy work in a supermaster. There is no blocker. Just we didn't implement that yet.
I've got a couple of comments just along the lines of like making it work more like other things. One thought is you've got the custom resources for virtual cluster and cluster version and things. There seems to be a lot of overlap in config there with the cluster API.
Yes, indeed.
It would be nice if as a user you could choose to use a virtual cluster or an external cluster with the cluster API with the same API.
Sure.
The other one was kind of the command line switches to the VCCTL command are a little bit strange compared to all the other Kubernetes flags. So maybe bringing those a little bit more in line with the other command lines.
Yeah, I think that is. I think that so the CTR tools is kind of pretty simple. So I think a child can simply repeat all the tests by directly use kubectl, no problem at all.
Mm-hmm.
It's just a very simple wrapper. Do a few magic things about setup to be
sure. Yeah, in general, it looks really good.
Thank you.
So Faye, in terms of namespace creation and namespace management, are there any restrictions on what a tenant can do in a tenant cluster?
There is a Chao, if you can show up, can you show up the namespace in the supermaster? No.
Yep, sure. So on the left-hand side, you see all the namespace on the.
So I give you some heads up. So maybe you see, so the way that we name it, you can see all the sync namespace has a pretty long prefix. I also add some UID part of 6-digit random character. This is solely introduced to avoid any possible name conflict in the supermaster. So that being said, there is a kind of a hidden restriction here. This prefix can be pretty long. So if you guys know that the namespace has a length restriction, so basically you probably cannot fully utilize the tenant, the length capability in the tenant.
Okay, so but a tenant can create their own namespace as long as it
Yes.
into the
The
length.
whole problem is, I think the current namespace length is 64, something like that. If you tenant create the full length namespace, the syncer will report an error because the namespace cannot be created in the super with a pretty long feature.
Okay. All right. One other question in terms of host isolation. What are your thoughts of managing that longer term? So right now, you said the focus is control plane isolation, which is great start.
Okay.
But,
so you are saying that the data plane isolation?
Yeah. So things like host volumes, or even like using like the host network thing. So are you thinking of any restrictions around those for tenant namespaces?
Restriction definitely. So certain things. So we have. So in terms of the host network, we have to make a few assumptions like that. What is the target use case? Because in virtual cluster, I talking more like service, the service environments. Certainly, the host network we shouldn't even allow the pod to access hosts. That's number one. Number two is in reality, if you really want to put these things, I mean, this is control plane only, but if you want to come up with any meaningful solution in the public cloud, so every pod most likely will have this own, VPC runs in the VPC environments. The bigger challenge in that regards is actually the service. In many cases, the pods cannot even possibly access the nodes in the public cloud. That part is we internally have some solution because we changed some we changed the Kubernetes proxy in some regards, but that part I don't think is good open source one because it's pretty like in-house forked. I think that will introduce more challenging in that regards is if in an isolated network environment, how do we make sure that all the Kubernetes basic service discovery mechanism like service class IP still works? That's pretty challenging. The isolation part, actually, I don't worry too much because at least in our use case, in that public environments, mostly you will use a sandbox controller like a Kata container or gvisor. Okay. So the isolation part, I don't worry too much because you have a VM, wrap over all the container processes. The more challenging comes up with actually is the networking setup for the service discovery.
Faye, I agree, and that's why I would slightly caveat calling this the hard multi-tenancy solution because this is not the complete hard multi-tenancy story. This is very cool stuff, but it is just this by itself is not sufficient hard multi-tenancy.
Sure. So that's the reason I'm saying that it's enabling. It's not actually yes.
Yeah.
It's just an enabling mechanism. I think this is kind of a prerequisite steps if you want to do that.
I'm not quite sure I followed what you were saying about cluster IPs for the services. I thought you said at front that all the tenants have to have the same CIDR block for the service cluster IPs?
So I want to make it clear. What I'm saying that is if you assuming every pod has runs its own VPC, if you use AWS, if you use inline network, so that I think in some cases rows traffic not even go through the host network stack at all. So the traditional class IP services is changing the host IP table, that mechanism doesn't work at all. So that's a challenge. That has nothing to do with the demo that I showed up today. I'm saying that if you want to run a sandbox environments in the public cloud, then you have a trouble that have the class IP type service work. Definitely load balance type service still work, but the class IP is a challenge. The class IP things I mentioned in this demo is that although we sync the service from the tenant to the super, but the class IP creation is still done by the tenant and the super separately. So the class IP in the tenant and the super are different. So although the class IP in the pod still works, but from tenant, they may see a little bit confusing because in my API server, I see my service is this class IP, but in the pod, I see the environment variable saying that class IP is that IP. So there is a little bit confusing in that regards. That's what I meant. We can somehow work around this, but we need more work to work around this because we cannot just simply copy the class IP from tenant to super because the IP can conflict. So in that regards, we have to make sure the IP is kind of created in a super and populated back to the tenant and involve some complicated things that we haven't done yet.
Thank you.
Hi, this is Dan from Red Hat.
Yeah.
I just want to say, yeah, it's really cool. Great job, guys. I had a question. So how does this model support resources that want cluster-wide scope, such as OLM or the cluster autoscaler, for example? Can there be certain tenant namespaces that are privileged and can see beyond their tenant master? Or if not, like how do you support something like a cluster-wide API service?
Cluster-wide API service, can you be more specific? I think everything can be done.
So I've looked at the OLM a little bit. It sounds like just like the deployments in the
yeah.
They
try
get
another one.
synced to the supermaster, and then they point back at the Kubernetes cluster, the API server of the tenant cluster.
Yes.
So you should be able to when an operator or the OLM looks at CRUDs, it'll see the CRUDs in the tenant's API server.
Yes.
What about RBAC cluster role?
So RBAC is set up in the tenant at all. There is no RBAC in the soup at all because RBAC is an API server kind of the control things. We only expose the virtual cluster to user. So user, you can only access tenant master. They don't even know there is a super. Yeah.
All right. In the super Kube API servers, are there any admission controllers running?
I didn't run, as I said before. So if you want to run an admission control, I suppose you should install it in the tenant master. But in some cases, it depends on the use case. Someone may want to enforce a global admission control, but that is more about, supermaster cluster administrator want to do something that influence everybody needs to follow it. So which means even if your tenant doesn't install a webhook or any control, I need to do my role. But the behavior like this is very slightly different. Is that in the old behavior without a virtual cluster, you probably get an error message to say that this pod cannot be admitted because there is a admission failure. But in our model, there is a slight difference if that really happens because the pod is actually created in the tenant master. But the object is created, but the pod cannot be started because they cannot be created in the supermaster. Instead, our syncer will report an error message to say why they cannot be created in the supermaster and populate it back. From tenant, they probably see a slightly different behavior is that the object is in, but it just cannot be running because it's still in a pending state.
Yeah, got it. So my question is now, what is the user experience when the syncer fails? What does the tenant user see?
So tenant user will see the object is in pending state.
But does it get the error message in any way?
Okay, that is a different issue because our syncer first we want to make sure if the keep first we have the HA setup for the syncer and the syncer we don't have assumption that the syncer needs to be 100% keep running, but we do want it to keep up running. All we can do is we cannot guarantee that it's always running. What we can do is once it's come up back again, they will try to sync everything again, and make them consistent, fix all the possible inconsistency. That's all we can do. We cannot, guarantee that the syncer is always 100% online.
Sure, but it's given the scenario we're talking about, there's a situation where whenever the syncer runs, however many times it runs, it's going to get the same error every time. Seems like there ought to be a way to get that error back to the client user, or the tenant user.
Say it again. So you are saying that if the syncer is,
if every time the syncer tries to create the pod copy on the master Kube API server rejects it because of the master has some admission control, it rejects it. There's a consistent error message that ought to get back to the tenant users somehow.
Yes. That's what, at this moment, the syncer will probably the reason why the pod cannot be created back to the tenant. So that's best we can do. So we cannot enforce to delete those tenant object at this moment.
My question was, where does the tenant user find this error message?
Oh, it's in the events.
Thank you.
This is super cool. In the last, not taking up the last 2 minutes, but how can folks get involved? Are you ready for contributions?
Yes.
Yeah. What would be next steps for folks on the call?
Sure. I think in this page, I would say that if you want to contribute, first you can contact with me or directly file. Everything is here, so you can just file PR. Just go to the Git. We have just file PR, and just if you want to talk more, you can send me message. We can talk more offline.
Wonderful. Thank you.
Yeah, I think it's almost time. So Charles, maybe finish your last part of demo.
Yeah, let's see the nodes. So yeah, we can see that the node has been removed from the virtual cluster. Yeah, that's it.
Do persistent volumes get removed also?
The persistent volume is still there because we didn't remove the persistent volume claim.
Okay, so if you remove the PVC, does the PV go away?
It will, but not now.
Okay, thank you.
Mm-hmm. Okay, so that's all about our demo. Thanks.
Thank you.
Yeah, sorry, Andrea, I take over your time.
No worries, I can just give an update. Sorry, the one-word update for HNC is that we just released version 0.3. I'm busy updating the user guide, and once that's done, you can go play with it. That's it.
Yeah, and on the benchmarks project, I'll send out an update on Slack, so no need to take up more time right now.
All right, sounds like we're done right on the dot.
Okay, thank you everybody, and thanks and just feel free to